Hello and welcome back to Calculus 3, section 11.7, motion in space. So, we're going to take our curve, right, that we have, whatever, X, Y, Z. I wanted to put more. There we go. Better. And we have vector valued function r of t again. So r of t is f of t, g of t, h of t, parametric equations. And then we said that we can take the derivative of it. Well, great. If this line in space is the path which, let's say, a fly would take to go between 2 points, then what would its derivative be? If this one is path, what's the derivative? Velocity. Thank you. Thank you. So velocity, v of t, is simply the r prime of t, which is f prime of t, g prime of t, and h prime of t. Now you can also take the magnitude, and what do we call the magnitude of velocity? Speed. So magnitude of velocity is speed. That's f prime of t squared plus g prime of t squared plus h prime of t squared. So we can get the velocity. What do you get when you divide velocity by speed?
Tangential velocity. Unit vector?
Unit tangent vector, exactly. You see that this is just, this v is your r prime. R prime divided by its magnitude is the formula we just had for the unit tangent vector, right? So, yeah, we're just renaming things here. And now, what is the derivative of the velocity?
Acceleration.
Yes. So, a of t is going to be r double prime of t, which is f double prime of t, g double prime of t, and h double prime of t. And there you go. I hope you understand that I can just take this h out and all of this becomes a 2D. I can add another one for 4D, right? We can make this any D we want. We're focusing on 3D because it's Calculus 3. You can make this whatever dimension. And you already, I'm just going to show the picture from the textbook. This is the picture I had earlier with the circle, right? I drew this not completely, right? And we had a little bit different picture, but technically that's what it is. So I'm going to draw this quickly and explain. Again, this is a two-dimensional case for us to understand, and then for 3D you just add another one. For 4D you add another two, and so on. So what do we have? I know, I practice a lot. Practice makes perfect. Remember that. X and the Y. And we're going to start here. I'm going to have a vector this way, and that's my R of t. And then I'm going to have the tangent vector this way. It's R prime of t, which is the V of t. And then I'm going to have acceleration vector A of t. Go that way. You ever wondered about orbits? Yeah? You see where the acceleration is pulling? Right? It wants to go forward, and this bends it in. Keeps going in a loop. And now you can pick this everywhere. R. R prime. And all the accelerations go inward. And all of this is from R equals cosine t sine t. Corresponding velocity vector is negative sine t cosine t. And corresponding acceleration vector in blue is negative cosine t negative sine t. Please observe the black and the blue, first and the last line. Do you see they're both cosine sine, and the blue ones are just opposite signs? Observe it, all of these black and blue vector pairs, they're all the same in the opposite direction, right? All of these things have to click. We know that the vector has its opposite if you just change the signs, and you see them on the picture, right? Now you can go ahead and plug numbers if you want to figure things out. Now this happens everywhere, right? If you are trying to understand, right, when you are so this is a road, right? And over here you have a wet oil spill with some leaves on it, right? So the car coming in this way, so the car coming in this way, even though the road, right, curves, the car, when it loses the grip, the friction between the tires and the road, at this point here, let's say, it's the tangent vector, right? It's the tangent vector that shoots this way. Now the tangent vector is the velocity vector divided by the magnitude of the velocity. So it's the velocity divided by the speed. So that's the direction in which the car is going to go. There's a gorier example with the roller coaster. Now, is there anything else that we need to talk about over here? We can put the equations if you are interested. Ah, yes. Two-dimensional motion in gravitational field. So 2D motion in gravitational field. And the whole thing has what you are used to. Your vector r of t consists of x direction motion of t. So instead of using f and g, I'm going to use x and y. You know that each motion, right, can be decomposed in its components. And if you are stuck on a 2D, the only components you have are x and a y component. Now, if you remember this stuff well, let's write it. I'll explain the u0 t plus x0 and negative 1/2 gt squared plus v0 t plus y0. You know both of these equations. We can discuss the parabolic motion, for instance. X and the y. And you are going to have your initial vector here, v0. That initial vector can be decomposed in x and a y direction. And you have initial point, which is r0. The coordinates of r0 are u0, v0. And that's it. Now, velocity v of t is given as u0, right, for the x, and we have the v0 minus gt for the y. Now you know these equations from physics. We did not cover any new equations. What do you have? Your vector valued function r is the one that describes the curve, the path through which if you throw something, right, it's going to go in a parabolic motion. So now that parabolic motion has x component velocity always constant, hence the x component constant all the time. The y component of velocity depends on the gravity. So you have the initial velocity, which is given as x comma y, right? You have two components. Guys, if I just, there's a difference between dropping and throwing. If I drop something, there is no x component. That u0 is 0, right? If I throw something, I am giving it a vector v0, which has components of u0, v0 in x and a y direction. So this one has components, and we have the initial point. Again, it depends if I throw from the from 6 feet or 3 feet or right 2. So you have also the initial height. Oh, I just noticed. You haven't seen anything. Haven't seen anything. Holy nightmare. No hiccups. All right. Say something, man.
Well, it's
So you have your initial point from which you are launching an object or throwing or dropping, whatever it is, right? And you can see them in a position. Remember that R is a position. From here to that point there, right? Let's say. So if I throw this straight, right? It's just going to have the half of the parabola to go down, right? It went just down. It never went up and down. So you can have, it's way too much exercise. Put that. You can have a throw from the, like this, pew, right? So this is your x0, y0 point, which in position are captured in your equation. It also, anything you throw or launch depends on your initial x, y velocity vector, and then only for the y component you have the gravity term, which is the one that gets it to land. So as you can see, all of these concepts are worked out and they all make sense to be a part of the equation. Now when you take physics, you learn these decoupled, right? You learn one thing about the motion in x direction and then another thing in the y direction. What we did here is just we put them in the same vector and we call it a motion in 2D. So you have the velocity equation and you have the position equation up there. Now they also give you additional formulas and go forever to compute the time of the flight, the range, the maximum height. I mean the maximum height. You know that the velocity at the maximum height, the vertical velocity is 0, right? Because in order for object to come down, right, if I put it up, it has to go up and then it has to stop. And that's where the velocity is 0 and that's at the top. And then it changes direction and comes down. So even if I throw something across in a parabolic motion, you will see that the x direction is always constant speed. The height, if you look at the y, it just goes up and down. So when you have that situation, right, you can set velocity, the y component, equal to 0. And that will give you the time at which the maximum height occurs. And then you just plug that here to find that time, to plug there to find the location. So you calculate time first. Now they give you the formula for that in the book. I'm not a big fan of memorizing all of the formulas. It's just, try to see the concept. It's much easier if you know what you're talking about and just plug in that rather than memorizing additional 16,000 formulas for every concept that's there. And that's it for 2D. For 3D, you have to worry about the direction, which means that you guys are going to do a lot more trig to find this. Please note that all of this is happening in a plane. When I throw something, I really don't want to throw stuff anymore. When I throw something, it doesn't matter which direction I throw it in. It will always go in a plane, right? It's not going to go everywhere and then drop. The leaf, the piece of paper or something you throw and it goes all over the place, that's because of the air, right? And its shape and its mass, right? So it interacts with the air and then it gets all crazy. If you take a piece of paper and throw it in a vacuum, it's going to be the same like marker through the air. So the motion in 3D, you just have to figure out at which angle your plane is and adjust your equations. But again, those are unnecessarily complicated, I guess. So when you have your x, y, and z, and let's say this is the direction, which is, when you think of it this way, this is angle theta over here, right? And this is 0 degrees and this is 90 degrees, or pi over 2. This is on the floor. And you launch an object from here and it goes whee, and it falls right onto that line. So when you look at this shape over here, that shape actually looks this way, right? Now you have the blue axis. Let's call this axis W, whatever. It's going to be W, and you still have the good old Z. So you see that every 3D motion that you have, every 3D motion actually decomposes, collapses onto a 2D. Now the issue is that you have a 3D vector over here, the W one, and you just have to rotate the equations onto that. So if you're interested in these more advanced things, look it up, and we can definitely do more. Hello, honors. We can definitely compute the plane in which this happens and then figure things out. And that's 11.7. I hope you're not disappointed. We can take a look at an example from homework. So that we said that we computed some numbers, but concept-wise, we really don't have much to talk about. So let's see. Yes. No. So problem 38 says, let's see, do we have any golfers in here? Anyone likes golf? No? You like? All right, so let's see if we can work this. So you have the initial position for golf ball, x0, y0, to live at the origin 0, 0. And it's hit at the angle of 30 degrees with speed of 150 feet per second. Find find the velocity and position vectors, graph the trajectory, determine the time of the flight and the range and the maximum height and all of that good stuff. Well, great. What I have here is a clear parabola like this. The object starts at 0, 0. It's going to land somewhere. We'll figure that out. We also want to know the max height. And we know that this vector v0 is at 30 degrees with a magnitude of 150. So if you have a vector, now you need all of the equations, right? So that we can deal with this. So we start with the, let me just put this as initial velocity v0. So we need to find the vector v0. For v0, we have these two components. Oh, initial velocity v0 magnitude. Right, so now you hopefully remember that our vectors u0, v0 can be expressed as the u0i plus v0j. Those are the u0 and v0 are components of the vectors, but we can write it in the ij notation. And now u0 is the initial velocity, so it's a v0 magnitude times the cosine of 30, because that would be the x direction, and that's I, plus v0 magnitude sine 30 degrees j for the y component. So we have 150, cosine of 30 is very good, I plus another 150, sine of 30 is excellent, j. So we finally have our initial vector. So this is all v0, right? The initial vector v0. Given as 75 root 3 comma 75. So I and j components. So I have these guys, and this is your u0 component, and this is your v0 component. So x and y components for vector. Now, and I think that's, yeah, okay. So this is our initial velocity. Now, what you have is the formula for velocity vector in terms of time, which said u0 comma v0 minus gt. Well, your u0 is 75 root 3 comma 75 minus, now gt, this is done in feet, all right? So if it's done with feet, and the g is 32.2 feet per second, so 32.2 t, and this is your velocity. You can clearly see the acceleration would be 0. There's no acceleration in the x direction, and in the y direction it would just be negative gravity, which is exactly what the acceleration of the system is. And the only thing that it's left for us to discuss over here is the position function. Now, you can integrate this to get the position function, or you can just write it. the position function if you know all the players. All right, so the u0t plus x0, and then negative 1/2 gt squared plus v0t plus y0, the two equations for a motion. We have u0, that's 75 root 3, t plus x0 is just 0, right? Because it's you hit the ball from the floor. Negative 1/2, so it's 16.1, so negative 16.1 t squared plus 75t, and then plus 0. So this is your position. So here is the velocity one, and here's the position. Now if you want the max height, you are going to take 75 minus 32.2t and set it equal to 0. And the reason is the vertical velocity, the y component of the velocity, is equal to 0 when the object reaches the maximum height, because it stops and then it starts going downwards. So from here, t is equal to 75 divided by 32.2, which is 2 point something. What happened? 320? 329. So 33. Thank you. Seconds. And now that you have this, you will compute your r. So location of the max height is going to be, when you compute r, at 2.33. So you have your r at 2.33 is given as the vector of 75 root 3 times 2.33, and negative 16.1, 2.33 squared plus 75 times 2.33. So now whoever punches this in a calculator first is a winner. You're not gonna make it, man. Let's see. Oh, it was even up.
Yeah, 87.3 right.
Wait, the first coordinate?
For the first one, it would be 302.7.
I'm sorry, can you repeat?
302.7.
302.7, and the second one?
87.3.
87.3, thank you. Now, if you ever played golf, because I haven't, you have the concept that the ball is going to be on the ground, and you click the thing, it goes over there and ends up on the ground, right? You have the parabolic motion. Now, where is the half of that trip where it reached the maximum height, right? So what's the max range? Yeah, 2 times the x coordinate, right? If you think about it, see this, Max? It's exactly happening at L over 2 if this is the whole length that it goes. Now, this is a quick fix to solve that. It's not going to be like that if I'm to take the golf ball and throw it. Right? Because it starts with some height. It might get a little bit higher and then have much more ground to cover until it falls. In that case, not half. This is half because it started on the ground and it's going to end up on the ground. So the max height was midway. Now, is it all lost? If you can, no, because you have this equation with the square, right? This one over here, which will help you take care of the situations where you are not starting on the floor and ending on the floor. So the shortcut only works if you start on the floor and end up on the floor, and it's the max height happens exactly midway in the path. Physics has wonderful examples, like that's invisible ink. If you deal with physics, can you please throw this out? Thank you. Yeah. What happened?
It's like the walk of shame.
Outside? Every time.
Like when you leave, it's like the walk of shame.
So we're going to put a cannon over here, right? As you know. And when you shoot, it's going to be a parabolic motion, but it's going to end up on a step. So yeah, figure that out. So you can have a lot of cool configurations, especially in physics, right? So the one that we have is a really cheap one, right? It goes like this. So your maximum height occurs exactly at the half distance, half of the range, how far it goes. None of that holds, right? None of that holds. Right? This should be also clear, right? That the max happens there, so that's not. But see, the trick is over here, if you extrapolate into negative time, then from this point to this point is L over 2, and from this point to this point is L over 2. And you can find that time. So there are ways to work with these formulas. Sometimes I just say just use common sense, and you should be fine. It's physics. Come on. So yeah.
You just take R and set the y component equal to 0, and then you'd have two of them, but one of them would be
negative. Yes. And you can find from there. You can backtrack the length, and you can find how far it goes times 2, right? So this problem was very cheap in terms of that it landed to be exactly in the middle. So to find the range, to find the max height, to find the time of flight, right? So if it takes 2.33 seconds to reach the max height, the entire trip is 4.66 seconds, right? So there are things that you can compute for all of these. Just take a look at what's out there. Maybe even pick up the physics textbook and just try to write the entire problem from a physics textbook just using this notation. We haven't learned, if you took physics and you took kinematics of motion for linear, right? This is zero new stuff except the new notation. You put this in a vector and then you just do it as a vector. And also for the angular motion, right? Same formulas, same everything, just using a different concept. Your path is now theta instead of linear x, and you have angular velocity, which is omega, and angular acceleration alpha. And the formulas are exactly the same for both of those worlds, just depending on which way you are thinking of the path. Is it line or angle? So all of that works. That's it. I hope you're not disappointed. Right? Just say bye. There you go.